Recording in progress.
Hey guys, my name is Esperanza Valenzuela,
And my name is Kai Tarkington.
and we'll be doing a presentation on dissection proofs. So, what are dissection proofs? So, in a dissection proof, we're given a geometrical figure, and we're going to cut it up into pieces and then rearrange those pieces such that we form another figure, and we will rearrange those pieces through rigid motions. And since rigid motions do preserve area, it follows that the figure that we started with and the figure that we ended with have the same area. So to outline what we'll be going over, we will first start by talking about a little bit of history, and then we will state a definition and theorem that will aid in the proof of the Pythagorean theorem, and then some lemmas and theorems that will help in the Wallace-Wallace-Arron theorem, which is a crucial theorem in dissection proofs in two-dimensional spaces. And then we will use that theorem to prove the area of a trapezoid, and then the sign of sum as well. And then we will speak briefly about dissection in other spaces.
All right, so a little bit of history on dissection. One of the earliest signs of dissection was found in Mesopotamia around 800 BCE. In the 1800s, Henry Pedregal developed a proof of the Pythagorean theorem by dissecting the hypotenuse square into the leg squares. Fun fact: in an ancient Chinese math book, has a visual proof of the Pythagorean theorem in it. Dissection also appears in tangram puzzles, which you may remember from grade school. And it involves rearranging pieces of a square. All of this connects to the Wallace-Wallace-Arron theorem, which is based in 2D. However, as we will see later, it does not hold in 3D.
Now we will dive into a definition and theorem. So definition 1 is that if a figure A can be partitioned into a finite number of pieces that can be rearranged through rigid motions to result in B, then A is equal decomposable to B. And just to remind you guys, rigid motions are things like translations, reflections, or rotations. So suppose we have a figure A, and then we dissect it into those pieces, and we can rearrange those pieces to form B, then we can say that A and B are equal decomposable. And theorem 1 is that rigid motions preserve distance, area, and angles. Now that we have established that, we'll prove the Pythagorean theorem, which is just, we have a right triangle with legs AB and a hypotenuse C, and it states that A squared plus B squared equals C squared. So consider this polygon ABCDEF with the side lengths as such, and such that these angles are all right. Then we will dissect it like so. And when dissecting it, we'll make sure that these are parallel and these are parallel. Now we have these two figures, and notice that these two figures are the exact same. It's just that this shows the side lengths and this shows the points labeled. And also notice that all four of these triangles have legs A and B and a hypotenuse C. So by SSS, they are congruent. And so we know this is right by construction. So by CPCTC, the corresponding angles are congruent. So all these angles are also right. And then we know that this is right. So by the linear pair theorem, we know that that is right. And since this is right by the linear pair theorem, we know that that is right as well. Now we will translate this purple triangle, this dark purple triangle, like such that NE coincides with CB, and we know that they do coincide since that is A and that has a length A. And then we will also translate this light blue triangle like so, such that DN and AF coincide, and we know that they coincide since this length is B and that length is B by construction. And now we have this polygon right here. Now, we're going to say, it's important to note that these two polygons are congruent, are equal decomposable, I mean, because we just dissected them and then moved them around with rigid motions. So by CPCTC, we know that this corresponds to this, and that this angle corresponds to this angle, and this angle. And we also know that the angle sum of a triangle is equal to pi. And all four of these triangles are congruent. That's pi halves, pi halves, pi halves, pi halves. So the angle sum is pi halves plus alpha plus beta. And so subtracting pi halves from both sides results in alpha plus beta equals pi halves. So we know that this is right, this is right, this is right, and this is right. And we also know that the side lengths are all the same. They're all C. And since this is right, and this is right, and this is right, and this is right, we know that the opposite sides of this polygon are parallel to each other. Therefore, we can conclude that ZFNC is a square. And similarly, we know that the sides of this gray polygon are all B minus A. And then by the linear pair theorem, we get that that is right. And by the linear pair theorem, we get that this is right. And we already showed that these two are right. So we get that they have the same side lengths, the angles are right, and that the opposite sides are parallel. So we also know that this gray polygon is a square. So now we know that this is a square and this is a square. And we know that this big square is partitioned by these four triangles and this little polygon, this little square right here. So the area of this big square will be equal to the area of this triangle plus that one, plus that one, plus that one, plus the area of this square. Now recall that the area of a triangle is 1/2 times base times height, and the area of square is side length squared. And since all four of these triangles are congruent, the area of all four triangles is 4 times 1/2 times AB, which simplifies to 2AB. And the area of the gray square is B minus A squared, and that simplifies to A squared plus B squared minus 2AB. And the big square has side length C, so the area is C squared. So now we know that the area of the four triangles plus the area of the gray squared equals the area of the big squared, which is this. And that all simplifies to A squared plus B squared equals C squared, which concludes the proof of the Pythagorean theorem. We now state a few lemmas and a theorem that will help in the proof of the Wallace-Ballais-Gérin theorem. So lemma 1 is that a collection of n squares with total area y can be dissected into a single square of area y. We're not going to dive into the proof of this, but the reason why these lemmas and stuff are after the Pythagorean theorem proof is because we need the Pythagorean theorem proof to prove lemma 1. So basically, to give you guys an idea, we take two of these squares and we place them next to each other, and they will form a construction like so. And by the Pythagorean theorem proof, we know that that can go into one square. And so by induction, we keep doing it until we get one square altogether. And then lemma 2 is that transitivity holds for equal decomposability. So if A is equal decomposable to B and B is equal decomposable to C, then A is equal decomposable to C. Lemma 3 is that a triangle can be decomposed into parts that can be rearranged to form a rectangle. So if we have a triangle and we cut it up into pieces and then rearrange them to form a rectangle. Lemma 4 is similar. A rectangle is equal decomposable to a square with the same measure of area. So if we have a rectangle, so say we have a rectangle, we can cut it up into pieces and then rearrange those pieces to form a square with the same measure of area. And lastly, the triangulation theorem states that every simple polygon with n vertices can be decomposed into n minus 2 triangles. So for a quick example, we have a square with 4 vertices, so we can decompose it into 2 triangles. A few notations that we will use throughout the Wallace-Ballais-Gérin theorem is we're going to let AB represent the area of polygon B, and we're going to let ATB represent the area of polygon B after a rigid motion was applied to it. So now you may be wondering, what is the Wallace-Ballais-Gérin theorem? Two plane polygons are equal decomposable if and only if they have the same measure of area. Since this is an if and only if statement, we will be proving the forward and the backwards direction, starting with the forward direction. So we're going to let polygon B and C be equal decomposable, and B can be dissected into n polygons. And if you look here, you'll notice that those n polygons partition B. So the area of B equals the sum of the area of those n polygons. And we will now, so we have all n of these pieces, and we will apply rigid motions to each of those pieces to form polygon C. And since rigid motions do preserve area, we know that the area of the sum of those n polygons equals the area of the sum of those n polygons that have a rigid motion applied to them. And we know that that then forms polygon C, so the area is the same. So by transitivity of all of this, we know that the area of B is equal to the area of C. That concludes our forward direction. Now we move into the backwards direction. We're going to let polygon B and C have the same area, and we're going to suppose that B has n vertices. So we have polygon B. We can decompose polygon B into n minus 2 triangles by the triangulation theorem. And then by lemma 3, we can decompose each of those triangles into a rectangle. And by lemma 4, we can decompose each of those rectangles into a square. And by lemma 1, we can dissect all of these n minus 2 squares such that we form one square. So essentially what we did was we have B, and we decomposed it, dissected it, moved parts around to form polygon B prime, such that B prime is a square. So we have that B is equal decomposable to B prime, which is a square, might I remind you guys. And by a similar argument, there is a square C prime that is equal decomposable to C, such that the area of C prime is equal to the area of C. So by transitivities of areas, since these two polygons have the same area and these two polygons have the same area, it follows that the area of B prime is equal to the area of C prime. And we started off by saying these two polygons have the same area as well. That's why. So now we have two squares with the same area. So we know that their side lengths are the same. Therefore, we know that the squares are congruent. So trivially, B prime is equal decomposable to C prime, since we essentially don't have to do anything to get C prime from B prime. So now we have that B prime is equal decomposable to B, and C prime is equal decomposable to C, and B prime is equal decomposable to C prime. So by transitivity, we know that B prime is equal decomposable to C, which concludes the backwards direction of our proof. Now we will prove that the area of a trapezoid is B1 plus B2 times h over 2. So we're going to consider this trapezoid ABCD with B1, B2 being bases and h being the height. Then we're going to take the midpoint of segment AB and DC such that we get points E and F. Now we're going to dissect it like so, and it's important to mention that these three line segments are parallel by using theorems that we learned in our Math 161 class, such as Playfair's axiom. Then we're going to rotate this polygon right here counterclockwise by pi radians, such that AE coincides with EB, and we know that they coincide since E is the midpoint, so though they have the same length. And we will now show that I'm going to just draw a little construction. We know that this is congruent to this, this, and this by alternate interior angles and vertical angles. So we have that that is congruent to that. And then we also know that this is congruent to that, that, and that by a similar argument. So we have that beta is equal to that, alpha, beta. So up here, we know that this and this form a linear pair, so that must be pi. Therefore, that also must be pi. So this and this form a linear pair. By the same argument, essentially, a similar argument, we can show that this is pi as well, since those form a linear pair. And then I'm just going to mention right now that by construction, we know that that is pi halves. So by alternate interior angles, we know that is pi halves, and by the linear pair theorem, we know that that is pi halves. Now we're going to translate this right here like such, so that f prime j and fc coincide, and by a similar argument before, we can prove that they coincide by f being the midpoint of that and this corresponding to this. Then I'm going to hope you guys trust me on this, but following parallelism theorems and all that stuff, we can prove that this is pi halves. And we know that this is pi halves by construction. And we showed that those two are pi halves. And then by a similar argument to the one where we showed that this is pi and those are a linear pair, we can show that these form a linear pair, so that is pi. Therefore, we have showed that this is pi halves, that's pi halves, that's pi halves, that's pi halves, and that this is parallel to this. And since these form right angles, it follows that ij and hc prime are also parallel. Therefore, we know that ijc prime h is a rectangle. So by axiom S1, we know that DBC, triangle DBC, is similar to triangle DRF. And by the midpoint connector theorem, we know that they form a 2:1 ratio. So the height of this triangle is h. Therefore, the height of this one is h over 2. And then we can see that DG is the same as CF, as this right here, which we can see right here. So we know that this is h over 2, this is b1, and that is b2. And we know that the area of a rectangle is base times height. So we know that the area of this rectangle is b1 plus b2 times h over 2. And since rigid motions preserve area, we know that this holds, but really, we know that this trapezoid is equidecomposable to this rectangle, since all we did was dissect it and apply rigid motions. Therefore, by the Wallace-Bolyai-Gérin theorem, we know that the area of this trapezoid is equal to the area of this rectangle, which proves that the area of the trapezoid is b1 plus b2 times h over 2, and that concludes the dissection proof of the area of a trapezoid.
All right, now we're going to get into trigonometry dissection proof. Something that we need to know before this we get this proof started is the side angle side area formula, which is this formula that you can see here. It's essentially the 1/2 of the product of two side lengths, and then the sine of the angle between them gives you the area of whatever triangle that is. All right, the proof that we're trying to the trig identity we're trying to prove is going to be our sign of some identity right here. What we want to show is that this quadrilateral BCEG is equidecomposable to this polygon FBIKEH. And the reason why we want to know that it's equidecomposable is because by the Wallace-Bolyai-Gérin theorem, that means that we know that the areas are equal to each other, and maybe that'll tell us something about a sine and cosine identity. Alright, so first we're going to start by constructing our figure. We're going to start with two triangles, both right, both with a hypotenuse of 1, and we're going to let this angle here be alpha and this angle here be beta. And then using B2, we are going to construct congruent triangles, and such that GEH is congruent to CBA, and this triangle here, BGF, is going to be congruent to CDE. For the sake of making things a little simpler to say, any triangle that's congruent, we're going to let any triangle that's congruent to triangle ABC be called an alpha triangle, and anything that's congruent to triangle CDE, we're going to let that be called a beta triangle, just so verbally things are easier to understand. All right, and so one thing that's really important to understand is that the beta triangle and the alpha triangle are not necessarily congruent to each other. So we don't have necessarily that this angle CBG is going to be a right angle. So we have to compute that angle in order to solve for the area of it. And using the interior angle theorem, and then also A2, we're able to do a bunch of algebra over here, and we get that the measure of CBG is going to be alpha plus beta. And in solving that, we're able to now solve for the area of the quadrilateral BCEG. And so notice that we can partition this quadrilateral into two congruent triangles. Like you see in this figure. And we know that they're congruent by SSS since we have two beta triangles on each side, making CE and BG congruent by CPT CP. And the same going for CB and segment GE. And of course, we have that CG is congruent to GC. And so using that side angle side area formula that I was talking about before the proof, we can do some computations to solve for each of the areas of the triangle. And we ultimately conclude that the area of BCEG, of quadrilateral BCEG, is sine of alpha plus beta. Alright, so now we're going to start breaking apart this quadrilateral into different polygons. We're going to start out with a line that's parallel to AC. And by Euclid's, I think it's proposition 29, we know that this angle is congruent to this angle. And then again, we're going to construct a parallel line to AB, and we're going to let the intersection be called I. And we find that through parallelism and perpendiculars theorems that this angle here is right, giving us by AAS a alpha triangle. And so we can repeat this process with this triangle CKE, and we find again by AAS that this is a beta triangle. And then we repeat this process twice more to find one more alpha triangle and one more beta triangle, which now leaves us with this quadrilateral in the middle, MIKL. And so we need to solve for the dimensions of that. At first glance, it looks like it might be a square, but that's something that we have to prove and we have to solve. It turns out that it's not. It's actually a rectangle. We do know that it is that all of the angles right here are right, again by a bunch of parallel and perpendicular theorems, linear pair and such, that those are all right angles, so we at least know that it's a rectangle. And then we eventually find, using the definition of betweenness down here, that this segment right here is actually equivalent to, or is equal to, sine of beta minus sine of alpha. And then this segment right here, doing subtraction using the betweenness definition, we have that LK is equal to cosine of alpha minus cosine of beta. And now we have a basis to go off of for our quadrilateral MIKL. We know the dimensions now. We know what defines it. So we know how to prove that it's congruent to something. So now we're going to take all of those purple polygons out, the 2 alpha triangles and 2 beta triangles, and then our rectangle. We're going to put them aside, and we're going to mess with our original 4 triangles, our 2 alpha and beta triangles. First, we're going to start out with a translation over to the left and up of our alpha triangle, and then we're going to do something similar with our beta triangle, over and up. And remember, we can only do this because we know that they are congruent. We know that segment CB is congruent to segment GE. We know that segment CE is congruent to segment BG. And so we're able to push them up against each other like this only because we know that they're congruent. All right, and now we're going to start putting back those purple polygons that we have out here. And so notice that this point G right here, this point F and H are all the same original points that we did use. So we know already that GBF triangle is going to give us a beta triangle. Similarly, we know that GEH is going to give us an alpha triangle. And then we can construct line MG such that it's parallel to line BF, and we can, again, by Euclid's proposition 29, this angle is congruent to this angle. Again, with our perpendicular parallel theorems, we can tell that that's a right angle, giving us again AAS, a beta triangle. And again, repeating that process to create this alpha triangle GLE. We find that, and now all that's left is to see if our quadrilateral that we found the dimensions of earlier will fit in here. And if you do the computation, you can easily see too that this is sine of alpha, or sine of beta minus sine of alpha, and you can visually see here that this is cosine of alpha minus cosine of beta. So right now we just proved that we can fit, that all of these triangles fit together congruently, the area is preserved, which means this figure that we have here now is this polygon FBIKEH is equidecomposable to our original BCEG polygon that we have here. And so what do we know, what we can say when we have equidecomposability? That those two areas are congruent by the Wallace-Bolyai-Gérin theorem. And I'm sorry, or equal, not congruent. And so we're going to see what happens when we look at what those areas equal to each other look like. And so we already found our BCEG area, and now we need to find our polygon FBIKEH by separating or partitioning them into 2 rectangles. And obviously we can visually see what the dimensions are of these rectangles, and so we can easily compute that the formula for this polygon is going to be sine of alpha cosine beta plus sine of beta cosine alpha. All right, and now we can set them equal to each other because of the Wallace-Bolyai-Gérin theorem, and we get our trig identity. And that is the end of our proof for the trig identity, sum of sine. All of this up till now has been in 2D. So what about 3D? We mentioned earlier that in 2D the Wallace-Bolyai-Gérin theorem holds, but not in 3D. There's something similar to it in 3D. In the Wallace-Bolyai-Gérin theorem, you have equal decomposability if and only if the area is equal. But with 3D, we have a little added invariant. We have equal decomposability if and only if the volume of the two polyhedra are the same and the Don invariant is also the same. The Don invariant is just this complicated, scary stuff over here. This tensor X right here is just a relation. We're not going to go into what it is right now because that is well beyond the scope of our research. And but it is, I will go a little into it. This L is representative of an edge of a polygon. In this case, I think we're looking at some sort of cube. And then this theta, it's not really an angle, it's a dihedral angle, so it's a little different to compute too. And you can't really multiply or add an edge and an angle, right? And so it's not really multiplying or adding. It's just a relationship that we're not going to get into right now. But this relationship is bound by these sets of rules right here. And this allows us to simplify also our Don invariant. As we can see right here, let's start out with the cube example. We can count our edges 4, 6, 8, 12. So we have 12 edges, and then of course in a cube we have that the dihedral angle is going to be pi over 2. And so we repeat this process. We have it 1, 2, 3, 4, all the way up to 12 times. And by that second, I don't know if you remember, but by that second bullet point, that rule that we had, we're able to condense it all into this. You can pause the video and go back and convince yourself of that later. But this is a little example of the portion of the Don invariant. And so what about other models like the spherical or the HHPM? Dissection does hold there. It does hold there, but it's well beyond the scope of our research. And so we're not going to get too into it, but yes, in spherical and HHPM, it does hold.
So now to sum up everything that we've talked about, or almost everything that we've talked about, dissection proofs have been around for centuries, dating all the way back to 1800 BCE, and they do hold in Euclidean space, the hyperbolic half-plane model and the spherical model. It's just that in spaces that aren't Euclidean, they're a lot more complex. So like, for example, in the hyperbolic half-plane model, you have to use like a hyperbolic metric or hyperbolic motions. And in a spherical model, it's like a similar one, and the area in the hyperbolic model depends on curvature and stuff. So there's just like a lot of additives to dissection proofs in other models. And like Kai stated, in 3D spaces, basically the 3D version of the Wallace-Ballard-Gerard theorem is that figures are equal decomposable if and only if they have the same volume and Don invariant. And we can use these types of proofs to conclude congruence of polygons using area measures, and we can visually prove algebraic identities and theorems that we just automatically assume to be true in high school. And lastly, dissection proofs can help everybody, but especially younger people, help understand why these complex mathematical facts hold, which is why we chose this topic. Thank you.
Thank you.